Welcome. Let's understand basics of power transformer protections based on MVA capacity. Transformers are the most important main equipment in any power transmission and distribution network. The performance of the transformers depends upon how well they are maintained and protected against all possible fault conditions that can arise in the installation, in the network, and in the ambient environment. Transformers in a power system can be divided into three major categories. Small-size transformers, less than 1 MVA, these are used mostly at the distribution end. Medium-sized transformers, 1 MVA to 10 MVA, these are used in secondary substations of state utilities and plant incomers. Voltage ratings on the primary side can vary from 220 kV to 33 kV. The secondary side voltages can vary from 33 kV to 3.3 kV. Large-size transformers, above 10 MVA, these are used in primary substations of state utilities and incomers of large industries, like cement plants, fertilizer plants, etc. The primary voltages can be either 765 or 400 or 220 kV. Secondary voltages can vary from 400 or 220 or 110 kV to 33 or 11 kV. Many of these may have 3 windings. Transformer application could be power transformers or power auto transformers or regulating transformers or step voltage regulators or grounding transformers or electric arc furnace transformers or power rectifier transformers. Transformers have to be protected, both for external faults occurring outside the terminals of the transformer, as well as the internal faults occurring within the transformer. Normal overcurrent and earth fault relays are adequate for protection against external faults. Special relays like differential and REF relays are required for protection against internal faults. There are 3 major conditions of transformers in the present-day transmission system. These are overload conditions. These produce excessive heat, which causes rise in operating temperature. Every 10-degree rise in temperature, beyond the withstand limit specified, results in 50% reduction in life of transformer insulation. Single-phasing conditions. There are increasing incidences of single-phasing in transformers. The main reasons are poor maintenance of transmission lines and circuit breakers. Unbalanced loads. Any unbalance in the 3-phase currents of a transformer will cause overheating, even if the currents are within rated values. Certain level of unbalance can be tolerated by transformer design, however we have to care about unbalances more than 20%. Large unbalances can cause neutral shift, which may be harmful to end users. If excessive neutral shift takes place, there can be flashover in substation. Here, we will see protection of small transformers, less than 1 MVA. Bare minimum protections are envisaged, since economy of protection is the major factor in deciding the extent of protection. High set overcurrent protection, 50, used to protect from high-level fault currents, of the order of 300% and above. Always instantaneous trip. Low set overcurrent protection, 51, used to protect the transformer from overcurrents in primary and secondary side. Peak levels are normally around 140% to 150%. Normal inverse IDMT characteristics are followed for trip time. Under voltage protection, 27, this is a bus level protection. Pickup levels are normally 85% and below. Over voltage protection, 59, this is a bus level protection. Pickup levels are around 110%. Restricted earth fault protection, 64, normally provide on the star-connected side, for protection transformer from internal faults. Here, we will see protection of medium transformers, 1 to 10 MVA. Since the transformer is handling a higher power, and it is in a key location. Like the incomer of a substation or an industry, following additional protections are advised. A. Thermal overload protection. 49. Let us consider a case where a normal overcurrent relay, with pickup level of 140% is used. It should be noted that the transformer is in the overload region, between 105% to 140%. If the load is around 135%, the overcurrent relay will not protect, but the transformer will get hot and lose its life. Thermal overload protection will help in this case. It is also beneficial to monitor the overload conditions in the winding and the core separately. The copper portion will get hot faster. For a given overload current, trip time will have to be faster than that for iron core. B. Current unbalance protection. 46. This will protect transformers against heavy unbalances. In case of unbalanced currents, the negative sequence component will increase, resulting in overheating of transformers. It is advisable to have two levels of unbalance protection, one for alarm and other for trip. I2T protection. This protection is very useful for rectifier transformers, where the currents will be fluctuating. In this case, the energy dissipated for given overcurrent condition is set as trip limit. If this energy level is exceeded, the transformer is tripped earlier than the IDMT overcurrent tripped for the same value. Here, we will see protection of large transformers above 10 MVA. What we are talking about here are very large, bulk power handling transformers where the criticalities are very high. Consequently, more protections than those listed in previous slide are envisaged. The extra protections are in the form of differential and overfluxing protections, which are mainly internal faults. Overfluxing protection. 24. This is to monitor the flux levels inside the large transformer. If the per unit ratio of V by Hertz goes beyond a value 1.05, the transformer will go into an overfluxing condition. This will cause overheating, even when the currents are within limits. Hence the need to monitor separately. Voltage unbalance protection. 47V. Voltage unbalance in large transformers are good indication of a grid disturbance. Can be used as an alarm. Differential protection. 87. This is one of the major protection for large transformers. This protects the transformers whenever there is an internal fault. As shown in the SLD, this protection needs two additional sets of CTS, which are perfectly matched and have adequate knee point voltage to drive a relay measuring circuit. It should be noted that a differential relay should trip only for an internal fault. A differential relay should never trip for an external/through fault. For this reason, a percentage biased relay with dual slope facility will be the best choice. This will have a very good through fault stability. It may so happen that a differential relay can trip whenever the transformer is switched on. This is due to the magnetizing inrush current flowing only in primary side of the transformer. To avoid this, the relay should have a second harmonic restraint facility. Similarly, a fifth harmonic restraint facility in the relay will help avoiding a differential trip during temporary overfluxing conditions. Monitoring of earth fault in ungrounded transformers. In case of transformers, predominantly medium size, there can be installations where the neutral is grounded through an impedance or high resistance. In this, when an earth fault occurs, normal earth fault relays will not work, since the required relay operating current will not flow in the ground path. Consequently, a different method has to be adopted, monitoring the zero sequence voltage. The zero sequence voltage is a good indication of a neutral shift, which happens when there is an earth fault. There are two schemes for monitoring the neutral shift. One, use an open delta transformer and a low-cost voltage relay. In this case, the open delta transformer may become expensive. 2. Use normal star-connected bus PT, but with a relay which calculates zero-sequence voltage by numerical methods. Let's see advantages of numerical relays over electromechanical and solid-state relays. Numerical relay is more accurate, have less burden, wide setting ranges available, multi-functionality, smaller in size, field programmable, parameter display, system flexibility feature, many coordination tools availability, communication provision, remote control, have special algorithms, special protections, self-diagnostics features as well. Transformer protection plays a major role in ensuring reliable operation of power transmission and distribution system. This is a brief introduction to bring out the various protections required for transformers. The protections requirements can be defined based on size and location. Numerical relays offer better solutions for transformer protection. Thank you for your attention and time. More stuff coming soon. Don't forget to subscribe.